Thanks and welcome to my talk. I will now present joint work with Christoph, Amma and Tanja Schultz, performed at the Karlsruhe Institute of Technology. And it's about a gesture interface which tries to proactively actively correct its own errors. So as some of you in this session may already know, natural input modalities like gestures have become quite popular in HCI. So for example, to interact with large displays at a distance, to control head-mounted displays or robots at a distance. And usually how that works is that user input is interpreted using statistical models. And the consequence of that is that sometimes this input may be interpreted incorrectly. For example, because there's a mismatch between the classification model and the user's input. And those misinterpretations require some kind of error correction. And as we all know, this error correction can sometimes be quite cumbersome because we have to engage in meta-communication to inform the system about this error and then backtrack the interaction state to input what we actually wanted to say to the system. And in this work, we propose an approach for proactive error correction supported by the system. But before we look into that, let me take a brief look at the gesture task we are working with. So it's a picture categorization task where a picture and a category matrix was shown to the participant on a large screen. The participant had the task to assign the category to the picture by pointing to the corresponding matrix cell. And this pointing gesture was interpreted by a GestureRecognizer, and then feedback on the recognized category was presented on the screen. So, and as this GestureRecognizer sometimes made errors, the feedback did not always match the selected category. So, think of this task as a model for remote operation of a large screen, for example. For gesture recognition in this work, we deliberately used a quite simple setup, as we wanted to have a working recognizer which still makes enough mistakes, so which need to be corrected. So we extracted standard motion features from an inertial measurement unit placed at the hand of the user. We modeled each class with a Gaussian mixture model and used simple maximum likelihood classification. To estimate the reliability of the recognizer's output, we calculated a confidence score for each result as the difference in likelihood to the next best class. When evaluating the recognizer, we achieve a person-independent classification accuracy of 77%, which is kind of okay for this simple setup, but of course not that great, so we should expect quite frequent misclassifications of the gesture. We then first looked into the confidence scores to see to see whether they help us to distinguish correct from incorrect classifications, and we see that they give a hint on that. So for correct classifications, the confidence was a little bit higher, but the variance was so high that this difference was not significant. So still, the posteriors from the classifier still contain useful information for the error cases. So we see, for example, that for more than half of all misclassified trials, the second best result actually was the correct one. So using this information could somehow help us to recover from an error situation, but to identify those error situations, we see that the confidence score alone is not enough. So we need additional data to tap into this information source. Now, how does our approach to detect such errors work? So we have the user who's performing a gesture which is interpreted by the GestureRecognizer, and the GestureRecognizer yields a result which is shown to the user as feedback. Now we can measure the user's brain activity at that point with EEG electrodes to look for specific patterns which are typically triggered by erroneous feedback you perceive. And if such an error is detected, so we feed this EEG data to an error detector, and if it actually says, yes, I saw such an error pattern, then the system can engage in proactive error correction. So how does this error detection from EEG work? So we exploit the fact that the mismatch between expected system feedback and perceived system feedback causes characteristic neural processes in the user's brain. So these processes are called error potentials. They are triggered typically 200 to 500 milliseconds after the feedback presentation, and it's well known that they can be measured by using electroencephalography, so EEG electrodes. That means that when we are taking such an EEG input stream, we can automatically detect or try to detect those error potentials. So we extract a fixed window after the feedback presentation from the EEG signal. We perform some artifact reduction, use features in time domain, using data from 2 electrodes at the user's skull, and then perform person-adapted classification using linear support vector machines. To evaluate this error potential detection, we collected 2 data sets. The first one was collected in a validation experiment in which persons operated a brain-computer interface, so not yet the actual GestureRecognizer. For this experiment, we had 20 participants. Here, error potentials were triggered by simulated errors, which were artificially induced in the task. And for this setup, we achieved a classification accuracy to detect error potentials of more than 90%. And then afterwards, we performed another experiment using our actual gesture task with 11 participants. And here now errors were triggered by real errors from the GestureRecognizer. We used classification models trained from data from the first task and from using some adaptation data. And we achieved a classification accuracy of slightly more than 78%. So taking those 2 results together, we see that error potentials can be detected with reasonable accuracy. So now that this error potential detector is in place, we can now formulate an error correction strategy, which works like that. We have the GestureRecognizer taking the input from the IMU and yielding a probability estimation of the classes. We present to the user the first best hypothesis from this distribution as feedback. And if this feedback is actually incorrect, it will trigger an error potential. Hopefully we can detect this error potential using our error potential detector. And if this happens, we then inspect the confidence value of the second best result. And if this confidence is above a certain threshold, we immediately present it to the user as the new result or the new feedback. If the confidence of the second best result is below the threshold, we reprompt the user, so we ask him to repeat the gesture. Of course, you can think of several alternatives to this approach or variants. So we can adjust the threshold, for example, of this strategy, which we call the second best strategy. We can also set the threshold to infinity, which then results in what we call the reprompt strategy. So it will never use the second best result and always reprompt the user to input the gesture again. And for comparison, we also define the manual correction strategy, which does not rely on error potential detection, but which requires the user to give additional input to notify a correction attempt. To compare the effects of the different strategies, we performed simulation in form of a leave one out cross-validation, leave one session out cross-validation. To realistically estimate the effect of the strategies, we use real data from the gesture task from 20 participants and from the error potential experiments I talked about previously. So here's one example of one fold of this simulation runs. So as usual, we take all sessions but one to train the GestureRecognizer and evaluate on the remaining session. And on that session, we can calculate a number of statistics. For example, of course, the gesture recognition accuracy, but also the distribution of the confidence scores, the correctness rate of the second best in case of an error, etc. And using all those statistics, we can then assess the effect of the correction strategies. So to give you an idea of how the simulation model works, here's one example of how it calculates the probabilities of a successful correction for the second best strategy. So we do this by identifying all the cases in which a correct gesture is recognized after correction is applied. So this is, for example, the case if an error occurs during the gesture input, but the error potential is correctly detected, the confidence is of the second best is above the threshold, and the second best result is actually correct. So, and to calculate the probability of this case, we need this information which we collected during the cross-validation. And we repeat this process for all those cases. So, for example, another case in which we get a correct result if actually no error occurs. Nevertheless, there's a false alarm by the error potential detector, but we can still recover if the confidence of the second best result is below the threshold and the reprompt yields a correct result. So we take all this together to then finally derive two quality metrics for each correction strategy. Those are the corrected accuracy, which is the gesture recognition accuracy after applying the correction, and the correction costs, which is the expected number of additional gestures per input. In the table, you see those results from the simulation for the different strategies. And what we observe is that the self-correction significantly improves the accuracy above the baseline, which does no correction, but at much lower costs than the manual correction, which is of course still a little bit better because it doesn't need to rely on the error potential detection, which makes its own errors. But for example, if you look at the reprompt strategy, it's only 6% worse relative than manual correction, but at 26% lower costs. And looking at the second best strategy, we are still significantly better than the baseline system, but at costs which are less than half than manual correction. I should note that there is potential for more complex strategies for correction. So, for example, you can offer selective reprompts, which, for example, only give the 3 most likely results to the user for the second trial. And using such strategies, we can achieve a corrected accuracy of more than 88%. When generalizing those results, you observe that the success of the error correction depends on the performance of its components. So to quantify this effect, we looked at the benefit-cost ratio, which is the improvement in accuracy of a correction strategy compared to the baseline in ratio to the correction costs it implies. And the result of that you can hopefully somewhat see in that figure. So what we've done here is this is the benefit-cost ratio for different performance levels or accuracy levels of the GestureRecognizer and the error potential detector. And what we see here is that for a given accuracy of the error potential detector, the highest benefit-cost ratio is achieved for a medium gesture recognition accuracy. So if the GestureRecognizer is actually too good or makes very little errors, then nearly all detected errors are actually false positives. If the gesture recognition accuracy is too low, then the costs of correction outweigh the benefits, because after correction the result may likely still be wrong. Finally, we wanted to know how those simulation results transfer to a real HCI experience. So we performed a user study with online gesture recognition and online correction with different strategies. Only here the error potential detection was simulated with realistic misdetection rates to be comparable to what we saw in the simulation. We performed this with 12 participants, and we achieved the following results, where we see that the estimated corrected accuracy and the estimated correction costs from the simulation actually match quite well what we see in the user study. So this gives some validity to our simulation results. What we also did is we asked our participants to report about the different aspects of the preference for the strategies. And we got as a result that users widely preferred the automatic error correction over the manual strategies, but they regarded the different correction strategies somewhat different. So the second best strategy was perceived as the least strenuous and least tedious strategy, because it has the which corresponds to the lowest correction costs. where the reprompt strategy was perceived as the least confusing, most predictable, and most intuitive strategy, because it always behaves the same, probably. So both strategies have their merits, but in different domains. To conclude, we showed in this paper that it's possible to detect error potentials from EEG in a gesture task, that the error potentials can be used to trigger various self-correction strategies, that self-correction comes close to manual correction but at much lower costs. We investigated the generalization to different performance levels, and we showed in a user study that which supported the simulation results and showed the preference for the self-correction strategies over manual correction. Future work, we'd like to look in the evaluation of a full end-to-end system with online error potential detection to investigate complex interplay of all those components and to transfer to other applications which, for example, have more complex feedback modes or have different ways of correction costs, a number of classes which will probably influence results. So with that, I come to an end. Thank you for your attention, and I'm open for questions.
Great talk, Andrew Fowler from OHSU. I wondered, when you were going in that part of the flowchart where you were saying, like, is the second best option above some threshold? Did you consider the strength of that error potential in that decision? So, like, if you had a very strong signal that the first best was wrong, did that make it more likely that the second one was correct?
That would be great to have, but it's actually quite difficult. So the current techniques for detecting those error potentials are basically always binary classification. So is an error potential present or not? So for single trial, it's quite hard to estimate a very high or low error potential. So this works, for example, if you average over multiple instances, you could see probably differences to assess the likelihood, for example, of an error. But the current technique does not allow that. So that would be nice to have in the future.
Okay. Thank you.
Hi, Radu Daniel Vatavo from the University of Suceava. I have one, what I think it is simple but also maybe hard to respond question. So there is clearly some phenomenon that occurs in the brain that makes it respond in a way that you can pick up and use EEG signals. But the brain has this remarkable property that it adapts to stimuli, to similar stimuli that are presented over time. So my question to you, if you have users employing such a system over a longer period of time, say over consecutive days or maybe weeks, do you think you will still be able to pick up those exact EEG signals to make your system work? Thank you.
Yeah, very good question. So we didn't, but there are investigations on those error potentials which investigate those ideas, and there's indication that that they don't go away, those error potentials. So, for example, there are studies which try to repeat the effects several months afterwards, and they still are there. There are experiments which work with very high error rates, so you could think that errors are so common that people won't react that much to those effects, but the error potentials are still there. They are maybe a bit weaker, but they are still there and could still be detected.
Thanks.